this and full screen. Okay, so this is chapter 12, Chemistry of Solutions. And the outline you should have somewhere in your notes, kind of divides this in about 3 or 4 parts in terms of what is a solution. I think we all have a rough idea intuitively what a solution is, but we need to look at it from a scientific standpoint. And there is a page also in your outline which lists a number of terms that you will need to be familiar with. Here is the list, and we'll talk about them in a minute, but I mean they're pretty common in terms of what you would experience, but I need to talk to you about them in terms of scientific ideas and so forth. Solubility, I think we all know what some of these terms mean in terms of what they are. Some of the factors that affect solubility, you know, oil and water don't mix. Well, when you mix sugar and water or salt and water, but gasoline, say, and oil, you find them to mix. We want to talk about, well, why do they mix, you know? And so that's the purpose of the course, is to look at the interaction characteristics of these things that you know, you don't normally look at. Units of solubility, and we've done a little bit of that in the beginning of the course, where we looked at moles and molarity and how much substances will go into a certain volume. And so we'll go through these and be sure that you have a focus on what to study for the final. Okay, first topic, we'll start on just what a solution is, by definition of solution. Now, basically, it is a homogeneous mixture. Which essentially means that it has consistent properties throughout. So if you wanted to evaluate a solution for whatever reason you have, one of the characteristics that you would certainly look at would be defining how much of one component is dissolved in the solution and evaluate it through the entire solution. Now, one of the issues that is important in here is the types of solutions. And how you think about them. A solution is defined in terms of 2 parts. There's the composition of the solution. We better make that point. And I'll abbreviate solution, SOLN, frequently. It consists of 2 parts: a solute plus a solvent. The solute, in general, is the component in the lowest amount, and the solvent, of course, is the component in the greater amount. Now, one of the things you need to focus on here is that when we talk about a solution, we're not talking about just the solute, not talking about just the solvent, but the combination of these two is the solution. Scientifically, we will need to take both of them into context. Because when you talk about dissolving so many grams of a substance into a liquid, you talk about it in terms of 10 grams in 100 milliliters. Well, 100 milliliters not of solvent, but of solution. So that's the idea that we're going to be carrying through this. We will hit one concentration term where it is a little different in that we'll talk about an amount going into a weight of solvent, because temperature factors are extracted and you have to deal with it that way. But anyway, for the most part, when we talk about things dissolving in other solutions and stuff like that, making solutions, we talk about it in terms of the solution as a whole, and we'll do some other things with that as we go through. Now, in terms of the types of solution, it's very important that you note the solvent in here defines the state of the solution. That is, solid solutions exist, alloys, liquid solutions, which we're probably most familiar with, and gas phase solutions. The air you're breathing right now is a gas phase solution. And so when we dissolve a solute, and I'll repeat this a couple of times, solute into solvent, the system assumes the state of the solvent. I guess the easiest example I could give you is take a spoon of sugar and pour it into a glass of water and stir it. The sugar crystals will disappear, and the solution then is in the state of the solvent. And so the greater quantity of component in the solution mix is the state of existence. So that gives rise to about 9 different kinds of solutions. What if we did this? We had solid, liquid, and gas components, okay? So how many solutions can you make in the idea of using the 3 phases right here? Well, if we say solid in a liquid, okay? Solid in a liquid, the second component will be the solvent, okay? Let's see, solute in solvent. How about that? And just what I'm trying to do is just show you that there are about 9 different types of solution in that are based on the states of matter. So we can take a solid in a liquid, and we can take now a solid in a gas, okay? Smoke now is not a true solution. Smoke is floating around is a colloid, okay? You can see a colloid, but it's pretty easy to realize, and probably in your experience to know, that the air that you're breathing is a mixture of oxygen and nitrogen and other pollutants and whatever floating around. You can't see them, but it's all in the gas phase. Then we can take a liquid and a gas. Liquid and gas. This room's full of water vapor, okay? So we can take a liquid that will evaporate into the atmosphere, okay? And then we go back the other way. We can take a gas and a liquid. Second, like I say, gas bubbled into a liquid. Soft drinks have CO2 dissolved in them, okay? So that's a real easy example of gas in a liquid solution, okay? So we can have a gas dissolved in a solid, believe it or not. Gas, I guess the easiest one is automobile tires. Over time, gas will migrate through the rubber seal in a tire, and your tire will lose pressure. If you didn't drive it around and put air in it all the time, it would eventually lose its air. There are rubber tires are porous, and oxygen and air molecules will migrate through. So as they do, that's a form of solution. And then we have let's see, gas and solid and liquid and solid. That's a little harder to find a relationship of a liquid and a solid, and I think mud would probably be a good example. But that's a high viscosity solution, I would think. And then we got the liquid and the solid. Let's see, we got liquids, and the solids. Liquid and liquid, of course. Liquid in a liquid solution. Solid gas. Let's see, solid. We've got a gas and a solid, liquid and a solid. Oh, a solid and solid. Forgot about that one. Solid and solids are alloys. An amalgam. Anybody know what an amalgam is? Dentist calls them fillings an amalgam, and that's a mixture of silver with small amounts of mercury in it that keeps it from corroding, and it's not enough to cause problems, but it is a mixture of metals and other alloys, brass. You have steel. That's an alloy of iron and cobalts and other materials. Anyway, we probably missed one. Anybody help me out here? When you make solutions, you can make 9 different types in terms of the states of matter. Character of solutions. Now, as we go through this, we're not going to be talking about real complex solutions. You probably know, and it's common knowledge, that you can mix, say, 2 or 3 solutes in a given solvent. You can mix several salts, for example, and those are called multi-structured solutions. And we're not going to get into complex solutions where you have 2 or 3 solutes and you have mixed solvents. I use one mixed solvent in Chem 2 because the compound that I'm dissolving is not soluble in water, but it is in alcohol. So I'll make a solvent out of a mixture of alcohol and water and then dissolve the component. But our entire chapter here is going to be on what we call, now listen to, simple solutions. So write down under here SIMPLE solutions. So I built this acronym to help people remember some of the characteristics, scientific characteristics of solutions. S stands for same throughout, meaning homogeneous. So same throughout. Okay, that's pretty straight up. Okay, their interactions occur on the molecular level. That is, the solute-solvent interaction occurs on a molecular level. We'll talk about this in a few minutes in terms of electrostatic interactions and likes dissolve likes and things. Okay, so that is that. In terms of the mixture, the types and of the things, we have 2 types of solutions that we're going to look at: molecular solutions and ionic solutions. When we talk about molecular solutions, those are particles which dissolve but do not break apart. And I think you, in your experience so far, you know that if you put sodium chloride into water, it will break into cations and anions. So it has a different characteristic in its nature, but it is a type of solution. And there are, and I use the M in there, molecular solutions are types of solutions, and ionic solutions. Okay. P stands for any solution. It's a physical mixture. So you either stir it in to dissolve it, or you evaporate the water, say, during distillation. Those are physical changes. So what you say is the solutions are physically prepared and physically separated. So when we talk about physical nature or something, we do not change the molecular structure. You dissolve salt in water and then trying to recover the salt, you would evaporate the water, and you still have the water as well as the salt molecular structure. Now in chemical interactions, you get a new substance. Well, here you do not get a new substance, but an interaction takes place, and we'll talk about that as we go through those physical forces we talked about in the last lecture, the hydrogen bonding, the dipole interaction, and the London forces, and so forth. In general, when a solute dissolves in a solvent, we generally say likes dissolve likes. Oil doesn't dissolve water, but you can put gasoline in it, or you can put or alcohol and mix it in water. When we talk about that, it's the polarity and chemical structure of the solute is compatible with the chemistry of the solvent. And so we list this as likes dissolve likes. We'll say more about that in a few minutes, about factors that affect the dissolution. Dissolution is a term you need to get used to also. Dissolution means dissolving process. Okay, and at the end of a solution, there are equal phases. And we mentioned that earlier, that the solute takes on the phase of the solvent. But when it's all said and done, you have equal phases of the solute and solvent, whatever dominates. So equal phases. So we see now, of course, as I mentioned, the solute does not dominate. The solvent is the one that dominates the state of existence, so that you'll understand what that phrase refers to in the context. But anyway, trying to learn the characteristics of a solution is part of your study effort, and this acronym, if you practice it 2 or 3 or 4 times, you probably remember them easy enough. Simple solutions and that issue. Okay, now I need to go through the terminology of solutions. There is one posted on the website, so you can download the lecture outline as many times as you wish. So the terminology is pretty straightforward. I think you understand what solubility is. A capacity to dissolve. That's the solubility. So we'll start there and say solubility, by definition, is the capacity to dissolve. Some items do not have a high solubility, and they do not have a good capacity for dissolution. Or some do have a high solubility in a given solvent, and we say that it has a high capacity for dissolution and solution. Now, there are 3 primary factors that govern, and we'll develop these a little more. Factors governing solubility, affecting, now we mentioned one already, the tendency of the solute solvent to mix, and we call that solute solvent compatibility factors. So that when we talk about dissolution of a substance, we talk about it in terms of likes dissolve likes. Another one is a tendency to achieve a lower energy state or a higher degree of disorder. Now, this is a thermodynamic issue in that this. Could you close that door for me, please?
What did you say? You say easy?
That's good. Okay, dissolution tends toward a high degree of disorder. In the study of thermodynamics, they're divided into laws of thermodynamics. The first law deals with energy, and we looked at that in thermochemistry, first law. But the second law of thermodynamics deals with the concept of disorder. Everything has a tendency to move to a more disordered state. That's like a ball rolling downhill. You put a ball on the side of an incline and turn it loose, it'll automatically roll downhill. Well, it's a natural tendency to go to a lower energy state. Well, what this means in terms of solutions is that when there is a solute-solvent compatibility, the solute will mix with the solvent to the greatest disorder or the greatest degree of dispersion that it can possibly achieve in the space that's available. So that's why it becomes homogeneous in the distribution of the solute throughout the solvent. So this term, entropy, is a term that's used in thermodynamics to describe a state of disorder. And we're not going to deal with that in this course in the context of quantitative analysis. But please remember that entropy is a measure of disorder and is a term used to say, okay, this is moving toward the greatest or maximum state of disorder when the solution is being made. So that's maybe a new term to you, but I do want you to be aware of, its context. Okay. And then, of course, structure, temperature, and pressure. Structure. Temperature. So, of course, one factor that affects the dissolution of something is its structure. Something that's crystalline or packed closely together, it's harder to dissolve than something that's not crystalline. Something that has a branch type structure. Say you had a closely packed molecular structure versus something that has branches in it like this. This would be easier to dissolve because the accessibility of the solvent is higher here in this structure than it is here. So crystallines would be more difficult to dissolve. And that's what we're talking about in terms of structure. Now, temperature is an easy one. If you want to dissolve something, typically you'd try to heat it. And for molecular systems, increasing temperature will certainly increase the solubility. But in ionic systems like salts and things, that doesn't necessarily happen. The corrosion that occurs in your Mr. Coffee or inside your radiator of your car results from salts falling out of solution at high temperature. So increasing temperature lowers solubility, and it builds up crud on the inside of whatever you're coming in contact with in water. Pressure is easy. You increase the pressure, you increase the solubility at a given temperature. Soft drinks are an excellent example. Oh, and over here in temperature, a lower temperature increases solubility of a gas. That's why you put your soft drinks, beer, and whatever you in a refrigerator, keep it cold. So it makes the CO2 stay in solution longer. So that's kind of familiar to everybody. But anyway, these are the factors that go into whether or not a solute will dissolve into a solvent. Now, looking at the solute-solvent compatibility again, we have a little kind of equation that we use and explain this. When we have the solvent separated from the solute, you have an interaction between the particles in the separate containers. So if you have a solute, well, you SL, that's your solute, before mixing. So these have a certain interaction parameter. You know, they hold together in the can that you got them in. Okay? Plus the solvent, I'm going to make SV, and this is SOLVENT. Before mixing, the solvent has a interaction with its other solvent molecules and so forth. They're in the can. Now, we mix them together. If they will mix, we will produce a solute-solvent interaction. Actually, balancing the equation, you get two of them. Two solvent-solute interactions. Now, if you don't have a solute-solute interaction, it won't mix. And so we generalize this to say if the solute interaction or a solvent interaction is less active. That's what the inequality means. Is less active than the solute-solvent interaction. In other words, the particles of the solute will attract to the solvent better than the solvent to itself or the solute to itself. So this is the condition for dissolution. However, on the other side of that equation, we can simply say, and this is very generalized, the solute compatibility or interaction and the solvent interaction is greater than the solute-solvent interaction. In other words, the solute does not attract the solvent, and when they mix them together, oil and water is a good example, no dissolution occurs. So I'll try to squeeze that in there. No dissolution. There we go. No dissolution occurs. So it's a descriptive issue. There's no quantitative calculations to do in this course. Now, you do have situations in which you do have quantitative interactions where you'll calculate solute-solvent interaction parameters, and if they meet certain criterion, we'll go ahead and mix those together. But here is the extent of our attachment to the concept of the chemistry of solutions, in that you understand that if a solution occurs, it means simply that the solute has an attraction for the solvent and vice versa. Okay. Dissolution towards a high degree of here. Solution formation So when we say a solution formation tends to max disorder, this is an easy concept to understand. So that if we have a solid that's in a geometric ordered structure like a salt would be, then plus the solvent, in that solvent, what you would have is a equal homogeneous distribution, but the disorder and the spreading out of occurs because of the tendency to achieve the greatest degree of entropy. One in here has to do with structure, temperature, and pressure. We got one problem that we'll take a look at as we go through this. Let's talk about structure. Now this revolves around kind of the likes dissolve likes in terms of polarity and non-polarity of molecules. About polarity of things. One of them is alcohols dissolving in water. Good old down-home ethanol for making alcoholic drinks has a structure looks like this. There's an ethyl group and an hydroxide and hydrogen in here like this. Well, when you see an OH structure in, as we talked about last class about polar molecules and hydrogen bonding, this is a very strong polar structure, or dipole. Okay, in that it has a negative and a positive end. Well, if you add something in there that has a negative positive also to it, and this negative, well, of course the negative will be attracted to the positive and the positive attracted to the negative, and those interactions in this case would be hydrogen bonding, and so you would have a nice mixing of compatible molecules and it would generate a solution. And sometimes the interaction is so great that you can literally reverse the roles of the two items being mixed. That is, say the concentration of alcohol is greater than the concentration of water, and this gives you an alcohol / water solution. However, the compatibility of the alcohol to the water is such that we can continue to add water to it, and we can have concentration of water greater than the concentration of alcohol, and the roles of solute and solvent then reverse in this. So this is a solvent in this case, and this is a solute. And in this case up here, this is a solvent, and the water's a solute. So this is pretty easy to understand. When you go to the pharmacy and you buy rubbing alcohol, it's usually around, some of it is delivered 30% in solution, okay, and some of it is 95% in solution. Well, wait a minute, 30% in solution would make the alcohol the solute, but 95% in solution would make the water the solute, if you think about it. So, I mean, it's just a reversal of who's doing what, and it's just terminology concepts, and it doesn't have anything to do with any big picture issues. But if you want all alcohol, you'd probably go with 95%, but in some conditions you might not need that concentration. So that's what I'm talking about in terms of likes dissolve likes. Well, these are polar interactions. And these are electrostatic in nature, in that we have a plus attraction to a negative, whatever polarity of the molecule, one attractive polarity of the molecule in another case, and the compatibility exists. Now these are more of an intrinsic characteristic in terms of their ability to form solutions. If you had a large molecule, think for a second, I know. This is called T-butyl chloride. You can see the little T and the three methyl groups in there make a little cross T, and then you got your chloride in there, okay? And I use this in one of my kinetics experiments in Chem 2. And what we do is we drop it in water. Okay. Problem is, no solution is formed. So what do I do? Well, what I do with this is I add to that some isopropyl alcohol. So the isopropyl alcohol has both a larger organic end to it that will interact with the organic molecule over here. It looks like this, using your tetrahedral geometry that y'all know so much about now. So, and then you have the OH group over here. So this part here interacts with the water, and this part over here is organic interaction. And so I have a binary solvent that dissolves a target molecule, and then we can run the experiment, and we generate, well, we run the reaction and we study the rate of that particular reaction. But the idea is that we had to add something to be compatible with the organic end, and we had, and it still was compatible with the polar end addition. It all boils down to likes dissolve likes. Now you can get into things like motor oil and gasoline mixing together and go crazy trying to figure out why they interact. So let's keep it simple and say that's good enough for right. In general, at a specified temperature, an increase in pressure will increase the solubility. Of course, you got containers that you're delivering each of its components in. But simply said, at a specified temperature, an increase in pressure of a gas increases its solubility in liquids. Soft drinks, of course, is the most familiar example I could give you. But this is a rough statement of what we call Henry's Law. It simply says that solubility is directly proportional to the applied pressure. That is, of the gas, is directly proportional to the applied pressure. And in an empirical relationship, we simply use S proportional to the pressure of the component. And if you recall how we dealt with the proportionalities in the gas laws, this is treated the same way, in that making this into an equation requires us to insert a proportionality constant here times the pressure. And this will solve for the proportionality constant to be the solubility over the pressure, like that. Now, the problems that you have is we know we're given the solubility at a pressure 1 and asked to calculate what the solubility at a pressure 2 would be. So that means that the K value, being constant, is the same for pressure 1, solubility 1, and pressure 2 and solubility 2. So that's what a constant is. So if K1 equals K2, then we can simply say that solubility of case 1 using our applied pressure 1 is equal to the solubility of the second case and the pressure of the second case. So you'll be given 3 of the 4 variables and solve for the unknown, typically the solubility. And we look at case 1, we'll say solubility 1 would be, of course, the 27 grams per liter. So we'll say 27 grams per liter solution. Okay? And pressure 1, of course, is the 1 atmosphere, 0.0 atmosphere. Then solubility 2 is the objective of the problem, as you know, and so pressure 2 is 12 atmospheres. So it's solubility 1 over pressure. Solubility 1 over pressure 1, solubility 2 over pressure 2. Substitute your values and solve for the unknown. So we have 27 grams per liter per 1 atmosphere to equal the unknown solubility 2 at 12 atmospheres. So that's pretty straightforward idea. And then so I'll come over here. Solubility 2 is then 12 atmospheres times 27 grams per liter divided by 1 atmosphere. And it's easy to see the atmospheres will drop out of this very 324 grams per liter. Did everybody see that okay? All right. Now, the problem is acetone and acetylene, okay? Well, I could change that to water and CO2 or anything. So it's really, the mechanics of the problem is that you identify case 1, case 2, and substitute and solve for the unknown. So that's very straightforward in my opinion, and you shouldn't have any problem covering right here. It's kind of a weird term, but what colligative properties are properties that are affected by the amount of solute in a solvent. Okay, so as you increase the amount of solute within a solvent, the main thing that's going to happen is you're going to change the vapor pressure of the system, and it's called vapor pressure of solutions. And so we need to first understand the concept of vapor pressure of solutions and how that is affected by putting components into a solution. Colligative properties. These are, again, properties of solutions affected by concentration of solute. These include what we call a vapor pressure lowering factor, so when you put in a solute, it interacts with the solvent and keeps the solvent from evaporating, which lowers the vapor pressure, and so the effect is called vapor pressure lowering. Okay. You also have an issue, boiling point elevation, freezing point depression. I make two items. They're the same, but they work off the same concept. But this would be easier. You are familiar with buying radiator coolant or antifreeze for your car. The formulation of a coolant or an antifreeze is to either increase the boiling point so that it doesn't boil at high temperatures due to the engine operation, or have a very, very low freezing point so that it doesn't freeze and crack the block of your engine. So this is what this idea is generally about. The formulation of solutions that have higher boiling points and at the same time lower freezing points, and we'll get to the technology here in a few minutes. And the last one in here is the osmotic pressure. And this is a membrane osmotic pressure in that it is a tendency to cause dilution of concentrated systems, and the migration of solvent is the pressure caused by the migration of the solvent against the membrane increases the pressure, and it's called osmotic pressure under certain circumstances. We'll talk about technology in just a minute or two as we get to it. But first thing I want to talk about here is concentration concepts and review a couple of these that you're going to need. And we've talked about things like molarity, whereas moles of solute dissolved in solution. Well, it's generally the same thing here, but we're going to introduce a couple of new solubility concepts here that you'll need for the problems that we're going to work. In general, concentration through dissolution is defined as the amount of solute divided by the amount of solution. Now, in this, please note in the amount of solution, this is a combination of solvent and solute. So when we talk about concentration of 10 grams per liter or something of that nature, is 10 grams of solute and a liter of a combination of solution. Now we will look at a concentration term that is an amount of solute in a mass of solvent. Primarily that's used because in temperature changes it is better to use a term that doesn't change. If I had mass over volume of a solution and I heated it, the volume's going to expand and that's going to dilute the solution. So nothing constant. But if you have a mass in a certain constant mass of volume, you can heat it all day long. The mass solid ratio will always stay the same. We'll get to it, and I'll show you how to use that when we get there. So let's look at a couple of problems that you will be responsible. Okay, so here's some types of concentration problems you're going to be looking at. Let's say you're given a problem where you are dissolving 25 grams of sodium chloride into 150 milliliters of water. Okay, what's the solubility in grams per milliliter? Well, in terms of this, it's just simply solubility is simply the mass of solute, 25 grams of sodium chloride, divided by the 150 milliliters of solution.
Don't you have to convert that to liters?
Milliliters.
You don't have to convert that to liters?
Okay, so we express it as 0.17 grams of sodium chloride per milliliter of solution. Okay, that's one simple example. It's not anything earth-shaking that you can handle that, I hope. Here's another one. From this same problem, calculate the percent concentration of NaCl in the 150 milliliters solution. Assume density of the solution equals 1 gram per milliliter. So you'll have to have density. Typically water by itself is 1 gram per mil. And if you have a light, what we call a diluted solution, then the density is usually assumed to be 1, and the mass can be calculated, and you can calculate a mass-mass ratio. So if we have 150 milliliters, and we'll use the 25 grams that we had up here, then the mass of NaCl is 25 grams from problem 1, and the mass of solution, both solute and solvent, is 150 milliliters, of course, times 1 gram per mil, which of course gives us 150 grams. So the percent is part over total times 100. The percent NaCl is of course 25 over 150 times 100%. Looks like 16.7% concentration NaCl. Okay. The idea of molarity. Okay. And you recall that is a term, capital M, molar, And molarity is a density term, if you've forgotten that. It's an amount over volume. So you remember density is mass per unit volume. Well, the mass in molarity is the mole. So we identify this as moles of solute per volume of solution, but it's specifically in liters. Okay? So that's just, it is the simplicity of the terminology molarity, and it's used extensively, as you know. So calculate molarity in simple problem. We'll use the one we just did, okay? All right, of 25 grams NaCl, that's, okay, we'll need that to convert to moles. Okay, calculate molarity of 25 grams of sodium chloride and 150 mils and 150 milliliters of solution, okay? Straightforward problem, just follow the definition of molarity. So capital M is molarity in terms of sodium chloride is the moles of solute. So we need to calculate the moles of solute. Well, how do you convert grams to moles? Well, simply divide by the formula weight, something we learned in the beginning of the year. So I have 25 grams divided by 58 grams per mole, right there. And then we have to divide by the volume of solution, but we have to express it in liters since it's in 150 mils divided by 1,000, and we have 0.150 liters. And so this will, grams will drop out, and we'll have units of moles per liter, which is the molarity. And so this is a 2.87 molar in NaCl, aqueous solution. Now, in calculations we did a while back, I'm just going to strike a nerve here. Remember that from this relationship, we can calculate moles by multiplying both sides by volume in liters, and that moles of solute will equal molarity times volume in liters. Now this is what we refer to as solution data. And we're working solution data problems. You give an equation, and in the problem, say 25 milliliters of HCl mixed with 30 milliliters of 0.9 molar NaOH, and you calculate the moles from the data and plug it into the ratio of the equation and whatever they're looking for, like that. But I just wanted to remind you that this definition of molarity leads to a very important relationship that is used extensively in stoichiometry reactions. So please check mark that and kind of keep it in the back of your head as we go forward in this. Okay, so that one you're familiar with. Now, two new terms that we need to cover. One is molality, M-O-L-A-L-I-T-Y. It is represented by a lowercase m here. It is defined as the amount of solute in a kilogram of solvent, a very special concentration term used when temperature changes are taking place. So a molar solution, lowercase m, is the mass of solute per kilogram of solvent. the mass of solute in here is actually moles. I always say mass because moles, mass, same thing. Moles of solute per kilogram of solvent. Like that. Okay. Let's say okay. So we want to find this as a LaLT, molality, lowercase m, is equal to the moles of glucose divided by the kilograms of water. That's all it is. And so we have 5.67 grams of glucose, which is divided by 180. Divided by that water, 25.2 grams, is 0.0252 kilograms. Solvent, 1.25 mole solution. So we've talked about three concentration terms, and you will be responsible for it. This is probably a new one to you, but we'll show you where it's used in just a few minutes. Mole fraction of solution components. This is a percentage, except we don't multiply times 100. And you calculate the moles of each component divided by the sum of all the moles. So a mole fraction of a component is moles of component divided by total moles of the system, in the system, of all the components. So here I'm giving you 30 grams of ethyl alcohol or ethanol, and there's your formula. You calculate your formula weight from that, and we're going to dissolve it in 150 milliliters of water, 1 gram per mil, still whole. What's the mole fraction of ethanol in the solution? So we have to calculate the moles of ethanol, moles of water as a solvent, add them together, and that's your denominator. And then you divide that into the moles of ethanol. And you'll get a fraction, a decimal fraction. And that's referred to as the mole fraction. One thing about mole fraction, when you put it all together, the symbology would be a capital X like this. That'd be the mole fraction of, say, component number 1, ethanol, if you want to call it that, plus the mole fraction of component number 2, which in this case would be a solvent, is equal to, and always equal to, 1. The sum of all, it's like a percentage. If you figured the percentage, you would add them up and it'd be 100. Well, this one is not added up, not converted to percentage, but left in mole fraction, but it is fundamentally the sum of all the mole fractions will always give you a 1, like that. Okay, well anyway, moles of ethanol, ETOH, be good enough, is 30 grams divided by, so moles of, this would be 46 grams per mole for the ethanol. .652 0.652. Good enough. Okay. All right. The moles of water is 150 grams. So we have 150 grams. Formula weight of water 18 grams per mole, and so we have 150 divided by 1/8 is 8.333 mole. The sum of moles is equal to 0.652 plus 8.333 total, which gives me 8.985. And so it's a, like, again, percentage, part over total. Well, here's your total moles down here. And so the mole fraction of ethanol is equal to moles ethanol divided by moles of ethanol plus moles of water. And so moles of ethanol is 0.652. Moles will cross out of this, divided by 0.985 total moles. Everybody okay on that? Part over total. And so the fraction of ethanol 0.073 is the mole fraction of ethanol. Well, in passing, if you want the mole fraction of water, and since the sum of these two equals 1, then I can take 1 minus the mole fraction of ethanol to get the mole fraction of water if you want to add that to it. So that's 1 minus 0.073 9274. I'll just stop at 7 because the sum of those two have to equal 1. So we have the mole fraction of water and the mole fraction of the ethanol. Okay, this is really where colligative properties kick off, and we look at vapor pressure lowering, and boiling point elevation, freezing point depression, and then we'll finish with a topic, osmotic pressure. Okay, now we need to understand what vapor pressure of solutions are. Vapor pressure of a solution is essentially the vapor pressure of the solvent in contact with the solution. Vapor pressure of the solution is partial pressure of solvents. It begins to evaporate. The solute is not coming out of the solution, so it's going to deliver the solvent only into the vapor phase. It's the partial pressure of solvent in contact with the surface of the solution. Now, the effect of solute in solution can be either to increase vapor pressure, in some cases it does, or decrease vapor pressure. We're going to exclusively work with decreasing vapor pressure and not the increasing vapor pressure. If you consider a container with a solution, whatever the issue is, here you start out with a pure solvent, and the solvent can evaporate molecules. Okay, so we'll have solvent particles in here. Now, if you put in a compatible solute, you now have particles all along in here that are bonding. And I'll draw a big one here, a couple, three. These are bonding within each other, holding the solvent. Say this is the solvent, and these are the solutes. And so these are all bonding together, okay? And what happens is the solute binds electrostatically or physically with solvent and reduces, by holding it into the solution, reduces its ability to evaporate. And this, as a result, results in a lower vapor pressure than the pure solvent. Okay, now that's the general principle. You know, you pour something in to a dissolve something into a solvent, it's going to interact to the point where it's going to retard the evaporation of the solvent into the vapor phase. Vapor pressure concepts of solutions are governed or described by what is called Rayout's law. And keeping it simple as I can, Rayout's law says that the vapor pressure of the solvent above the solution, and I'm just going to call that vapor pressure of solution. So the vapor pressure of the solution, which is actually the solvent over the solution, is equal to the vapor pressure of the solvent, pure solvent, times the mole fraction of the solvent. Like that. So the more the less solvent versus more solute you have, the lower the vapor pressure. Okay. Now, what this is showing is an ideal, the trend of vapor pressure, okay, as the amount of solvent mole fraction increases. So of course the solute concentration mole fraction would go down as this one went up. So there's kind of a seesaw effect here going in that direction. But this is the ideal trends in an ideal solution. And so the calculations we're going to do are going to follow the trends in the ideal solution. So what does it mean? As the mole fraction of solvent increases, okay, the vapor pressure increases up to, here is 100%, so to speak, or mole fraction of solvent is 100%. Okay, and so the vapor pressure right here would be the vapor pressure of pure solvent. Okay. Well, this trend is a linear trend. This is what this curve defines. Is vapor pressure solution is proportional to vapor pressure of the solvent times the fraction, and it's a linear curve. That are straight line, y equals mx plus b kind of thing. Anyway, the questions that you'll run into will be calculate the vapor pressure of a solution. Now the problem is that the mole fraction of solvent is difficult to identify, but the mole fraction of the solute is easy to identify, you know, in a problem and in laboratory activities. So what we want to do is we want to write Rayout's law equation in terms of vapor pressure of the solvent and of mole fraction of the solute. Okay, I'm going to write. Okay, jot down Rayout's law, and this will be for an ideal solution. Okay, the equation I gave you earlier is a statement of Rayout's law of an ideal solution. The vapor pressure of a solution is equal to the vapor pressure of the solvent times the mole fraction of the solvent. Also, and I mentioned this earlier, and this is why we need to understand mole fractions, is that the mole fraction of solvent plus the mole fraction of solute write it out, is equal to 1. Okay, that's simple enough. I showed you that earlier. Okay, now if I take this as a simultaneous relationship, and now I have mole fraction of solvent here and mole fraction of solvent here, then I can take this equation and solve for solvent. So I'll have, and then substitute what's left into the equation. I'll have it in terms of solute. So the solvent, if I had to subtract mole fraction of solute from both sides of this equation, the mole fraction of solvent will equal to 1 minus the mole fraction of solute. Now this is then substituted into the equation here. And we get the Rayout's law in terms of vapor pressure of solvent and mole fraction of solute. So this would then become vapor pressure of the solution to equal vapor pressure of the solvent times 1 minus the mole fraction, of the solute. Like that. Now distribute the vapor pressure of the solvent through the parentheses, and we have the final form of the vapor pressure of solution formula. It's easier to to measure out solute than it is to get the mole fraction of the solvent. So the equation in this form is much, much easier to work with. Now, note in here, accent this, vapor pressure of the solution is not a colligative property. Now, you hear me? Vapor pressure of the solution is not a colligative property. Vapor pressure lowering, anything that you do to change the vapor pressure or the properties of the solution, is a colligative property. And so this part, if you'll notice, here's the solvent. And in the beginning I said, well, our solution with the solute is going to force the vapor pressure down, or you're going to have a lower vapor pressure. Well, this part of the equation is called the vapor pressure lowering factor. So if you've got the vapor pressure of the solvent, the mole fraction of the solute, this in itself will tell you how much to subtract from the vapor pressure of the solvent and give you the vapor pressure of the solution. So I'm going to take you through a problem right now. Okay, keep me having to waste time writing all this stuff out. Okay, here it's got two problems in here. One, calculate the lowering factor, and then calculate the final vapor pressure. So, but what is the vapor pressure lowering of water when 5.67 grams of glucose is added to 25.2 grams of water at 25 degrees? Okay. Now we know that, and then it says, goes on, what is the vapor pressure of the solution? So, kind of give you a comprehensive look. Vapor pressure of the solution, of course, is going to be the vapor pressure of the solvent minus the vapor pressure of the solvent times the mole fraction of the solute. And this part back here is the vapor pressure lowering factor. Now we're given the vapor pressure of water at 25 degrees up here. So what's going to happen is when we get the lowering factor here, we just simply subtract it from 23.8 by putting it right here. So that's pretty straightforward, I hope. But what we need to do is calculate the mole fraction of the solute. And so here is the grams divided into so many grams. And you recall mole fraction is moles of the component of interest. This is our, and this is glucose. I'm going to just GLU, if that's okay. Divided by the sum of moles solution components. Okay, so if we get the moles of glucose, we have 5.67 grams at 180 grams per mole. So convert to moles, divide by formula weight. Okay. Moles of solvent, which is the water, is we have 25.2 grams, 18 grams per mole. 25.2 grams divided by 18 grams per mole. It's like 1.4 mole water solvent. Okay, so the moles glucose plus moles water, of course, is 0.0315 plus 1.4 mole total. That gives us a 1.432 total moles. Okay, now what do we need to do? We need to get the mole fraction of the solute, and then we can plug it in and get the answers, right? So the mole fraction of the solute, which is our glucose, is the mole of glucose over the total moles. And the moles of glucose are 0.0315 moles glucose. And that's divided by 1.432 mole total. And so our mole fraction. Okay. So now that we have the mole fraction of the solute, and we know the mole vapor pressure of the solvent from the problem was 23.8 millimeters of mercury. Right there, then we can take vapor pressure. All right, we'll do it the way the problem says. Vapor pressure lowering would be the vapor pressure of the solvent, water, times the mole fraction of the glucose. So that's 23.8 millimeters mercury times 0.022, and so the vapor pressure will go down by whatever that product is. .524, 0.524 millimeters. Okay, so that is the vapor pressure lowering factor. So now if I want to get the vapor pressure of the solution, and I'm fixing to lose my equation up there. I can rewrite it. So we want the vapor pressure of the solution. That's the vapor pressure of the solvent minus that vapor pressure lowering factor. So just to emphasize this, the 0.524 millimeters would go there. So vapor pressure of the solution now is, what was the beginning vapor pressure? 23.8 millimeters minus 0.524 millimeters. And so the final solution pressure (23.3). And in some applications, that's a significant drop in vapor pressure. Now, problems on the exam will be just as exact as this. There won't be any major surprises or curveballs on this. It's pretty straightforward if you just learn the procedure. I will have one that will simply ask for the vapor pressure lowering, so be cautious there. And then I'll have one that will ask for the solution. So you'd have to calculate the vapor pressure lowering and subtract it from the solvent vapor pressure. So check mark those as you study and make sure you're conscious. Okay, there's your phase diagram for water. As you recall, the region is a vapor pressure temperature relationship that defines state of existence of water. Solid, there's ice, liquid, water, gas, vapor, or steam. So we have here, and I'm going to move it up here, solid in this region, you have liquid in this region, and all this region under here is, of course, gas phase. Okay. The lines, as you recall, are the transition conditions. Like if we wanted to talk about freezing, would be a liquid-solid transition, say right there. And if we want to talk about boiling, it would be on that line, and that would be a liquid-gas transition. Well, as we define boiling point, it's the temperature at which vapor pressure is equal to the atmospheric pressure, and our atmosphere is 1 atmosphere, or 760. So what I'm going to do is go right across here, draw a line. I'm going to use a little color here to emphasize a couple of things here. So I'm going to come across here, and this will be the normal vapor pressure of 1 atmosphere, or 760 millimeters. Can you see that okay? That's our 1 atmosphere, standard atmosphere. Then from that, we're going to come straight down to the temperature axis, right here, and then over here, do the same thing. These points represent the normal freezing point, 0 degrees in terms of Celsius, and the normal boiling point, 100 degrees. Okay, so this point right here would be 100 degrees Celsius, and then this point would be 0 degrees Celsius, or 32, or however you want to look at it. So these are, again, normal boiling points and normal freezing. Here. Okay, now that's for pure water. If a solution is made and the vapor pressure is dropped, okay, then boiling has to go to a higher temperature because it's harder to boil. And so what happens when you have a solution made, the phase diagram will shift. This is, the blue lines is for the pure water. Make a note of that. Okay, the red line is going to be your solution. What happens is the triple point will shift down toward the axis down in here. I'll try to be neat about this so you'll understand it, hopefully. And so this kind of coincides back in this direction. It shifts down. And it also brings the forks down so that it is parallel to the forked lines. Go up here, and it'll parallel back up here to, and this is exaggerated. It doesn't do this wide a spread for nominal solutions that we work with. All right, now what I'll do is I'll extend this line at atmospheric pressure. Now it's still going to boil when the vapor pressure of the solution gets to the vapor pressure of the atmosphere. But because of the more difficult to get the solvent out because of the presence of the solute, you're going to see, let me move this up so it won't over. You'll see a different boiling point and a different freezing point right here. See how it shifts? The normal freezing point was here. The normal boiling point was here. But now we shifted out to these points out here. And so I drop a line down to the axis. I'm going to get some better red. See if this works. Yeah. There you go, that looks a little better. Look at this boiling point jump up to here. So now the solution are your red lines, and this is a new freezing point. I'm going to call that TF prime right there. And over here we have a new boiling point, and this is of the solution. And the event that shifts this upward in that direction or downward in this direction has a specific term, as we've got up here. This is boiling point elevation. And this one right here is freezing point depression. Hope you can translate DEPN as depression. Okay, so you now have new freezing points and new boiling points because of the solution that was made. The distance between here and here can be calculated. That change in temperature right here is called a delta TF, which is the freezing point depression. And over here, this one is the delta TB. That's your change in boiling point. Now, each one can be calculated using a very, very simple formula. The delta T, the change in freezing point, is called a freezing point depression constant, K, for water, times the molality, concentration in terms of molar system. Now, why would I use that? Remember, it's moles over kilograms of solvent. Well, this entire concept involves changes in temperature. And so you need a concentration term in the equation that will be constant or for a given mix. The delta TB is the same type of calculation. New boiling point elevation is a KB, boiling point elevation constant, times the molality of the solution. And you recall, I'll write it up here, molality. Now, I'm not going to write it right there. Let me move it up a little bit. Molality is moles over kilograms of solvent, just to remind us what's going on. Now, the water, will be the problem we'll be using. We'll put glucose here in a certain molal solution into water. Now, different solvents have different changes in freezing point and boiling. I don't know if you can see this or not. This is from the Ebbing text, and these are, let me see if I can focus that a little better. Not too bad. Maybe you can see that. Okay, different solvents have different boiling point and freezing point depression constants out here. So we're working with water. The boiling point elevation constant is 0.512, and the units are degrees C per molal solution. So I'm going to come down here and write KB for water is equal to 0.512 degrees C per m molal solution. And the freezing point depression constant is 1.858. So KF for water is 1.585 degrees C per molal solution. Of course, you'll have those tagged in the problem, so you can, okay, so we want to take, let me jot the problem. Okay. All right. Okay, we're not going to have to calculate the molality on this one because it will save time. I've already done that. Given 0.0222 molal solution of glucose in water, calculate new boiling point and freezing point. Well, the normal T freezing point for water, is 0 degrees Celsius, and the normal boiling point of water is 100. So all we need to do is calculate those changes and add or subtract as the case may be. And so from 100 degrees C. like that. And then we get the thing. Now understand and try to remember that it is the change that's the colligative property, not the final answer. So when we get the new boiling point, new freezing point, that's not a colligative property. It's the change that we're adding or subtracting that's a colligative property. And the same way with vapor pressure. The final vapor pressure of the solution that we make is not the colligative property, it's the change in vapor pressure. So just emphasizing that for your enjoyment. But anyway, first one is to calculate the freezing point depression. So we'll go delta TF equals KF times the molality. Well, we're given the molality somewhere here, 0.0222, and here's the freezing point depression. Constant is 1.58 degrees C per mole. So here we have 1.585 degrees C per m mole times the molality, which was 0.0222 mole. And so that change in temperature will be 0.0222 times 1.585, 0.035 degrees C. So this will drop the temperature by 0.035 degrees C. So I'm going to go ahead and do the new temperature, which would be 0 degrees normal minus the change in temperature, 0.035 degrees C, and so a new is a minus 0.035 degrees C. So there is the new freezing point. Now the change in boiling point is done the same way, KB times the molality, which is, and here's our KB number, it'll be given 0.512 degrees C per mole solution, and 0.0222, sorry, 222 mole. Molalities drop out as they did before, and so .011 degrees C increase. Now this is the colligative property. Actually, it's not a new change. I'm sorry, that was wrong right there. Erase that delta T new. The new temperature boiling point or freezing point. So T new freezing point, or new, I'm off the page, yeah, I'm going to come it up a little bit. New boiling point is equal to 100 degrees C plus the boiling point elevation, 0.011 degrees C, which is 100.011 degrees C. There and there are your new temperature values here. I'll let that smolder for a minute. I cut it off. It cuts off faster than people like. Okay, osmotic pressure is the pressure generated by a solvent trying to dilute a concentrated solution across a semi-permeable membrane. Okay, here's what let's see. Osmotic pressure has a symbol capital Pi, is what is usually shown on that. And so I'm going to start there, save us some pencil work. Osmotic pressure is the pressure exerted across a semi-permeable membrane a semi-permeable membrane to dilute a more concentrated solution. The issue is if you have a semi-permeable membrane. I'll tell you, one is a sausage packet. If you've ever bought links of sausage from the meat company, they come in these little white wrappers. So those are semi-permeable membranes. And I can take one and fill it with a salt solution and put it in a bucket of water, and it'll just expand, and burst. Okay, because the solvent is moving in through that semi-permeable membrane. A semi-permeable membrane right here allows fluid to flow in one direction but not the other. And so if you have a high concentration salt on this side, and so you got particles, a lot of particles over here on this side of the membrane. Okay, and then you have a low concentration or simply the solvent on this side. The flow of fluid will be toward that concentrated solution, and the pressure that's exerted or that is caused by that flow on the backside of this membrane. See, it won't go back the other way, but it will push it's kind of like a balloon. Starts at this, and you have your fluid going in through the membrane. Well, this membrane's going to start expanding like that, and then it's just like blowing up a balloon. And in order to do that, you have to apply an inside-out pressure, and that inside-out pressure is osmotic pressure, inside-out pressure. Does that make sense? Kind of, because that's what the cells in our body function. Okay? In biology, you learned that the cell, the biological cell in animals, is what we call isotonic with respect to blood plasma. That is, if you have a cell, it's typically about 7%. You got 7% salt on the inside of the cell, and the plasma outside is also a 7% salt, and that's what we call isotonic in context. However, if the outside becomes highly salt, you start drinking a lot of seawater, for example. You have a cell that's 7% like this, and you have a plasma whose concentration of salt is greater. Let's put salt concentration. Concentration is greater than 7%. The plasma inside of the cell is going to tend to try to dilute that, and it's going to go out here, and the results is the cell will shrivel up and you die. Okay. Or if the inside of the cell has a higher concentration, greater than 7%, and make a bigger circle. Isotonic. If the concentration of salt in there, and the plasma will send fluid in, and it'll act like I showed you earlier. It'll function to bloat the cell. It'll cause it to build up and has a potential of exploding. it will burst. You can blow up a balloon with enough air, it'll pop. Well, the cells will do the same thing. If you lose the salt in your bloodstream, runners sometimes get to the point where their bloodstream doesn't have enough salt in it, and so they just kind of lose it. That's why you take salt pills in hot weather, because you sweat. Well, that's coming from your blood plasma, and so that's causing your cells to all of a sudden start sucking more fluid in, and you got a problem. But anyway, I can't remember which one's hypo and which one's hypertonic. I think this is hyper and that's hypo, but I'm not going to ask you. Now, vapor phase osmometry, again, is used to determine molecular weights, what we call intermediate size or molecules of polymers. Polysaccharides is a good example. Now, how is this done? Well, the osmometry equation, osmotic pressure equation, is very simple in its look. Pi equals mRT. Okay. Of course, pi is the osmotic pressure. R is the gas constant, 0.08206 liter atmospheres over mole Kelvin. There are other R values, but that's the one you would want to use. Temperature is Kelvin. Okay. Go ahead and copy that down. I'll wait. Bink. Start out with the pi equals mRT. Now, this is molarity. Now, what's molarity? Okay, that's moles of solute over volume of solution expressed in liters, remember? And then you have your R constant and T in Kelvin. Well, what we need to do is find formula weight in this expression right here in moles. And moles, as you recall, is the mass of the solute, or whatever you have dissolved, divided by formula weight. And so what we want to do is substitute in here for moles. We'll have mass in grams divided by formula weight times RT divided by the volume of solution in liters, and all that's equal to the osmotic pressure. Now that looks kind of weird, but all I'm going to do is solve for the formula weight and then plug in all the existing data. Now you can simply memorize the equation if you want. So to get to this right here, I'm going to start here, pi times volume. I have to do things in parts and pieces. That's mass over formula weight, RT. Then I can take formula weight, multiply both sides, and I'll have my formula. I'm lead. Formula weight now is equal to mass in grams times R times T divided by osmotic pressure, which was 1.47 millimeters. Osmotic pressure divided by volume expressed in liters. So go back up here and check our data real quick. Okay, so we're given 0.582 grams. I'll fix that. 0.582 grams, so that's 0.582 grams right there. R is 0.08206 liter atmospheres mole Kelvin, and our temperature is 21 degrees and 273, 4789, 294 Kelvin. So we need 294 Kelvin put right there. And then the osmotic pressure is 1.47 millimeters, but it has to be converted to atmospheres because the R value is in atmospheres. So I divide that by 760 millimeters per atmosphere right there, and the volume 106 mils is 0.106 liters. I know it sounds kind of busy, but it's really not. MRT can come to this, and all you're going to have to deal with is this equation, MRT over pi volume. So the data should fit this, but remember, I'm going to give you the pressure in millimeters, so don't forget to divide right here by 760, okay? R value, it'll be 0.08206. And so, simplifying this, I'm going to invert this ratio, and I have 0.582, 0.08206, then invert multiply 760, and that's divided by 1.47 and 0.106. It all comes out in grams per mole, and that is the answer we're looking for. I get 232.9 grams per mole. That seems sure to the brilliance of one of my students. Thank you, dear. So putting the 294 in times 294. Yeah, that's much better. Yeah, 68,484 grams per mole, and you'd probably see it on the test rounded to probably 69,000 grams per mole based on a couple of sig figs or something like that. So whatever's closest to the answer that you get, you would select that one.